So welcome to the reading group today, and thanks for joining. So for today, we'll be talking about our recent work, and I will be co-presenting with Emma uh, Kondrup from McGill and Mila, who is also working with me on this project and a few other projects. So today we'll be talking about our large language models, good temporal graph learners, and I will hand it to Julia for the speaker intro.
Sounds good. So yeah, we're happy to have Emma and Andy today. You pretty much probably know all Andy. So Andy is Shenyang Huang from University of Oxford. He's a postdoctoral scholar at University of Oxford now, and he obtained his PhD from McGill University and Mila, focusing on temporal graph learning and supervised by Professor Raihani Rebani and Professor Guillaume Robousseau. He's interested in representation learning on temporal graphs, anomaly detection, and graph representation learning. And he was the organization chair for the Temporal Graph Learning Workshop at NeurIPS 2022 and at KDD 2025. His previous research includes change point detection on temporal graphs, COVID-19 disease modeling with temporal contact graphs, and link prediction on temporal graphs. He also enjoys writing Medium blog posts about temporal graph learning. And then Emma Kondrup is a research intern at Mila, supervised by Professor Rayani Rabani and a research assistant at CBIL at University of Copenhagen. Her research interest lies at the intersection of AI and law, particularly in health. And on the technical side, she focuses on graph machine learning with a special interest for temporal graph machine learning and applications of machine learning for misinformation detection. And we're very happy to have you here. And I hand over the mic.
Yeah, thanks for the kind introduction, Julia, and yeah, thanks for reading the bio. Now I realize how long usually it takes for me to read the bios as well. So a bit of uh, different point of view. So at today's talk, we'll talk about how to use language models, large language models on temporal graphs. And as I mentioned, I will co-present with Emma. So we'll break down the talk into two parts. So I will talk about the background, the motivation, how we get here, and then Emma will give you more details on the methodology and the experiments. So this work is a joint work um, uh, between different collaborators, and we have the slide here to show. So the TG Talker team, which is the framework name that we have in the paper, is by me and Ali and Emma, Zachary, Zifeng, Michael, and Rehane and Guillaume. So it's a large collaboration between different universities, from Cambridge to McGill, to UDEM and Oxford and many more. So yeah, so I will get started on the background and motivation first. And feel free to stop me if you have any questions or if anything is unclear. So now, and this is not news to anyone. So now we are in the deep learning revolution phase, where we see a lot of practical use cases for different machine learning models, and some of them are starting to become indisposable in our life to do various tasks. So very recently, there is the release of GPT-5. And these large language models are changing how we view, extract, and organize information. And the key breakthroughs in the LLMs are motivated and fueled by the transformer architecture, which is highly scalable in terms of you can just throw more GPU at it, and it can scale to much larger model size, and also in terms of the large amounts of training data. So training on basically as much of the web graph data as possible, like the web natural language data as possible. And so the motivation of the work really starts when I was at NeurIPS last year, and I got pretty bored. And I went to my hotel and I played it with some LM for a bit. So I was thinking about, so we have so much data that are large scale graph that we produce every day. So some statistic here. So we have 5.2 billion social media users, and that's about 64% of the total global population. And we have 7 billion messages being sent every minute on Meta platforms. And we have also about 500 million tweets each day. So these scales are very large, and this is such rich data. And how can we learn from all these data? Um, and basically, so I was trying out to ask questions to LLM and to see how well they can actually understand temporal graph data and how can we use it. So basically, there's a few questions to keep in mind, and this work is part of the series of work that we are working on to try to answer these questions. So the first one is more fundamentally, can we have foundation models for graph structure data? So we actually have very large scale graphs that are in production that people use every day, like the social media graph that we talk about, and also like during COVID modeling, like the contact networks. These are also million billion scale graphs. You also have transaction networks and so on. So can we actually learn foundation models for graph structure data? And more specific to this reading group and also to my research interest is how do we build foundation models for temporal graph data? So not only graphs, but graphs that are essentially ordered by time, right? So uh, temporal graph data is changing, it's constantly evolving. Um, and it can basically keep going, and you want to learn the past to predict the future? And what kind of benefits can such a foundation model bring um, to temporal graph learning and graph learning in general? So, so here's a motivation section and a background section on kind of towards temporal graph foundation model. So as I mentioned, so part of my research over the past 2 years have been trying to get some answers on this topic, right? So how do we build temporal graph foundation models, and how do we get there? So a first mandatory slide on what is temporal graphs and what is so unique about it. So basically, we have many real-world relations that are evolving and changing, and these are modeled by temporal graphs. So we have user interaction networks, we have temporal knowledge graph, and we have flight networks, right? And these are all changing graphs that we model as temporal graphs. And the benefits of a foundation model that we see in other domains, such as NLP and images and video, are that a foundation model can basically help you to avoid doing the following things, right? If we have a foundation model that works well, it can prevent us from training from scratch on every single data set, right? It can help us save time or completely get rid of hyperparameter tuning. So we don't need to fine tune the model to pick like what's helpful, what's not helpful um, for each of the data set, right? And we don't need to keep a set of weights for a single model for a single data set. If you want to learn and transfer and adapt to many data sets, uh, you should use a foundation model, right? And then for the last point is that this also basically reduces the bar and the requirement for domain expertise, right? So that's what we see with the foundation models from NLP. Like one of the key aspects and key reason for success is because basically it removes the barrier for individual user to have to train and keep their model, right? So you can talk to an LLM about anything really, and you don't need to think about how do I train it, how do I keep it myself, how do I fine tune it to my use case, right? So that's why it's very motivating to think about the idea of having a foundation model for graphs, right? And then there are also a bunch of benefits, right? So one thing is that for new data sets, you can directly provide inference. right? So that means that your time to inference is actually very fast. So you don't need to do any training. You don't need to wait. You don't need to get a large amount of GPU. You can just go directly to predict and check the results. It also can facilitate transfer learning. So I think particularly for temporal graph, there are things that you can also learn and transfer across data sets. So we won't touch upon that one too much in today's talk, but in later paper that we have in this month, we'll see that transferability part. And you can also adapt your foundation model across different tasks. So here it's more talking about the NLP foundation models where you have different natural language tasks and the model can perform all of them. I think on the graph side, it's still a open question on how to have a graph foundation model that can do different tasks like node level, link level, and graph level tasks. And for the final point is that you can also adapt your foundation model potentially across different modalities. So we have different type of graphs, right? So I mostly work with standard homogeneous temporal graphs. And for example, like Julia worked with temporal knowledge graphs. And there's people that are more researching on temporal heterogeneous graphs. So there are different type of modalities and challenges with each modality. Can we have a foundation model in the future that could try to solve all these modalities without having to manually engineer specialized model for every single modality? And can we also even transfer learning or transfer across tasks, across modalities? So these are interesting research questions and interesting idea to think about. Um, and yeah, and so that's also partly what motivates me to try to look into how do we use LLMs for temporal graphs as LLM themselves can already do all of these things on natural language tasks. And let's see how much it can do for temporal graph. Right. And one thing that I want to point out, and also this is my thoughts after going to KDD last week, is we are at a crossroad for thinking about graph foundation models. So basically, there's two distinct paths on graph foundation models that the community have been researching for the past 2 years, I would say, or even more. One is how do we adapt LLMs for graph data, or in our case, temporal graph data, right? So can we leverage existing pre-trained language model to perform graph level task, to perform graph task essentially, right? And the second path is can we design new architectures? So again, by new architectures, I mean these architectures should be designed to be a foundation model in mind, right? So not necessarily I'm talking about GNNs because we know GNNs have limitations and they're also very hard to transfer across graphs, right? So I'm more talking about how do we design foundation model architectures that are really suited for foundation model training, and how do we design algorithms that are suited to train foundation models on graph data. So these are the two branching paths. And right now, these are two distinct paths. Um, and I believe potentially the answer in the future would be a combination of both of them, potentially a multimodal foundation model, but it's just more thinking at this stage. So, and to position today's talk, I would like to think about these two paradigms that we can go down to achieve foundation model on temporal graphs. So for adapting LLMs for temporal graph data, there are some prior work already. And also, since I'm not like the domain expert on temporal knowledge graph, I didn't put in the various temporal knowledge graph papers that have been shown to get success from leveraging LLM for temporal knowledge graphs. But one thing to point out there is that temporal knowledge graphs, normally there's already rich semantic meaning in the connection itself. So you would already seen the nodes and the edges and the edge types. So the LLMs are naturally very good at them because they have probably seen them potentially during training as well and understand the semantic meaning and so on. And here I'm more talking about can we use LLMs to understand arbitrary temporal graph structure, right? And from that perspective, So there's three work that I want to highlight here. So one is LLM for Daiji. So that was published last year. So in that paper, they look at how does LLM perform on synthetic dynamic graphs. So the graphs are relatively small size, like very small size, and they are all synthetically generated. So the motivation is to see if dynamic graph is something that LLM can do, and also if it will serve as a good benchmark to test LLM capability, and that was from last year. And then there's also a REL LLM paper, which will be presented at next week's reading group talk by VJ and his co-author. So that goes down the line about how do we design, um, uh, how do we adapt LLM for relational deep learning, which is very related to temporal graph learning. And then for this talk, I will focus on TG Talker, which is a new framework for how to leverage LLM to directly process arbitrary temporal graph data. And on the other side of the crossroad, where we want to design novel architectures and algorithms for foundation model, we also have a talk coming up this month on Mint, which is on August 28th, which will be presented by Kia Rush, which I believe is also in the audience today. So on the Mint paper, we explore how do we take a standard TGNN that we have seen um, from the literature and design new algorithms and new ways to scale it up to train on more than one temporal graphs, but on many, many temporal graphs, and what kind of transfer capability that we can see from such approach. Um, and then there's also the REL GT paper, the relational graph transformer paper, that is kind of similar, doing similar things on for relational deep learning, where it can be served as a backbone as foundation model architecture to train on uh, different type of relational databases and different type of basically these temporal graphs that you get from the relational databases. Okay, so now I will talk about So how do we use LLM for temporal graphs? Um, and so basically I talked very briefly about this before. So in the work, we are referring to LLMs as pre-trained language models, and also they can be foundation model for text and images. Um, and they have textual reasoning capabilities as they have chain of thought and so on, and all these LLM research capabilities. Um, and there are also prior works on combining graph and LLM. Um, and the core question that we want to answer in today's talk and this paper is, can LLM understand temporal graph data? And in the bracket is out of the box because so can so how much does the natural language pre-training that we have on the LLMs already help us enhance our understanding of temporal graph without us having to fine-tune the model, do gradient backprop, right? So that goes back to the slide that we see before on the capabilities of a foundation model that we want. So we don't want to fine-tune it for every single data set. We don't want to fine-tune it for every single task. So how much can we get from just designing a good prompt and leveraging LLMs out of the box? Yeah. And some quick notes on prior work on LLM with graphs. So this is a Google paper from using LLM on static graphs. So basically, they talk about how you can encode graph with natural language and how you can ask a prompt question to the LLM. And here in this work, they focus on the prompt engineering and they focus on graph reasoning task. So they are working with synthetic graphs where they are trying to check if there are cycles, there's like how to count the node degrees with LLMs and so on and so forth. So more in graph reasoning and graph understanding task. And in the work today, we'll mostly focus on real-world tasks on temporal graph like link prediction, and we will also directly compare with TGNNs in terms of performance. Okay, and this is the other prior work, which is LM for Daiji. So as I mentioned, so this one more focused on synthetic temporal graphs, where these are toy graphs that are very small, like 10 or 20 nodes, and they are generated from synthetic graph generators, and their goal is to focus on temporal graph reasoning task, similar to the prior work where they are checking temporal paths, they are doing some counting, understanding time, and so on. And the conclusion from this work from last year is that LLMs can do well on some tasks, but would fail quite hard on some other task, right? So you can check that paper out for more detail. So this one of the prior work that I saw, like when I was working on this project as well, is how can we do the same level of testing, but on real-world temporal graph data set? Um, yeah, so we'll answer that in this work. Um, so in terms of the research question, so can we understand real-world temporal graph data out of the box? And that's why in this work, we focus on real-world temporal graphs from TGB and also some prior work that I did. And also we'll focus on link prediction tasks as this is the most common task with also the most selection of architectures that has been designed for this task, right? And we want to compare directly to TGNNs to see that how is the performance in relation to model specific or temporal graph specific models, right? And the second research question that I find very interesting from this work that kind of motivates on why you would use LLM to do temporal graph task, right? There are definitely drawbacks with LLMs in terms of the fixed context window size, right? And also you need to put the entire graph into natural language, which is just one way of representing temporal graph, right? And the motivation for here is that we want to ask the LLMs to also generate plausible explanations for predicted links. And this aspect I'm quite passionate about because this is a capability that is simply not possible on all the prior models. So all the TGNNs, temporal graph transformers, temporal graph neural networks, they are all black box. They just give you the output probability, right, from the decoder NLP. And it is basically impossible to ask TGNNs to explain why you make this prediction. Why do you assign this node specifically a higher probability to be the destination? And this is also very difficult to answer this question because we do not actually have ground truth in terms of explanations for the link predictions that we have on temporal graph, right? So there's no such data that's available. So like nobody really knows why a future link would appear. And with LLM for the first time, we show that you can actually obtain textual explanations for the predicted links. So you can directly ask LLM why you make such a prediction. And as we see in this work, for most of the cases, the LLM can give you a very plausible explanation. So here the emphasis is on plausible because we don't know if the explanation itself is actually the true reason behind the prediction. But what we do know is that at least the explanations provided by the LLM make a lot of sense and looks plausible and correct to human annotators, for example. Yeah, and basically our framework is that we take a temporal graph. We also have encodings, text encodings. So how to encode a temporal graph, and then how to ask questions on temporal graph, and then you feed it to the LLM, and the LLM will directly generate you the answer for which destination node it should be, as well as providing explanations for why it reaches that answer, right? So and before we go down to the methodology details, I will spend just like a few minutes more on the formulation of the task. So here we are looking at continuous time dynamic graphs, where you have a stream of edges, um, as you may be familiar. And in this case, you basically have more and more edges arriving. And your goal is to leverage all the information that you have until current time and make the prediction for the next future time. And with LLMs, we slightly changed the formulation of temporal link prediction because with LLMs, we don't need to do any training. We don't need to train any MLP for decoder and train TGNN for encoder. Basically, we just directly ask it in natural language, what is the destination node you think should be for my link prediction? So basically, the LLM task can be formulated as a question and answer pair. So basically, given a temporal graph, so let me just quickly go through this equation here. It's actually quite straightforward. So basically, what this is saying is that we treat the LLM as a function mapping from token to token. So from text to text, right? And the input of the LLM are two things. One is a textual encoding of the graph, which in the paper we provide one example way, but of course there could be many different ways that you can try as well. But basically here you would take the temporal graph and convert it into text. And then the second part is for my list of queries that I want to ask, um, I'm going to turn that query also into a natural language question, right? Um, and yeah, and basically we have the query encoding function, the temporal graph encoding function, and also yeah. So this is on the link explanation. So for the next part, once you get the answer from the LM, so this A here, which is the predicted destination, then you can also ask the LM to condition on the question, the query, and the temporal graph context and the answer to ask it about what is the explanation you provide for this prediction. Because here the A is not the ground truth answer. This is just a prediction from the LM. You can ask it, why do you make such prediction? And this is the link explanation part that we'll get through later on as well. Right. And now I will hand the mic to Emma, who will present the methodology for the paper. And also, if there's any questions, I will take one or two questions. I think there's a question from the chat. Um, whether the scalability of this talk would be a problem. For example, you have millions of nodes and the encoded embeddings would be huge. That is a very good question. So the scalability of this, so I will answer it in two parts. One is the scalability of the LLM. One is the scalability of the temporal graph. So the scalability of the LLM is limited by the context window. So there's only so much information you can feed to the context window. But through our experiments, we find out that for most temporal graph tasks, to get a good performance higher than majority of TGNNs, all you need are basically a temporal subgraph. So you actually don't need a whole graph as input to the LM. And you would take something like the past few hundred edges and also some temporal neighbors that we will introduce in the framework. And with that, you can already get really good performance. So from that point of view, the context window is definitely a limitation on the LLM part, but for link prediction tasks and perhaps different temporal graph tasks, it might not be a huge restriction if the model can already get good performance with the context window. And in terms of scalability on the temporal graph, so there's two aspects to this. So one is basically the receptive field. So as I discussed, the input temporal subgraph might not be that big, and it can usually get the job done. So that might be okay. Now, in terms of scaling to the number of query you want to predict, because for larger temporal graph, you have more edges that you want to predict. So this part, will depend on how fast your LLM inference can be. And in our experiment, we find that for most data set, it's like 1 to 2 hours. And then for the larger ones, it could be up to a day. But of course, if you have a super large one, then the number of query can also be very large. So that depends on how much compute you have and how much LLM that you can run in parallel to answer this. Because the LLMs don't also have to be processed in the sequential fashion. If you have a set of queries, uh, you can absolutely just distribute it across multiple LLMs to get your answers as well. Um, okay, yeah, thank you everyone. So I will hand the mic to Emma. So do you want to share your screen?
Thanks, Andy. Yeah, I'll do that. Can you see my screen?
Yeah, looks good.
Oh, great.
Okay,
Okay,
now
yeah.
presenter view actually.
Oh,
On the right side, we see the presenter comment. Yeah, this
okay, this might be better.
this is good. Yeah.
Cool. Great. Okay, yeah. Well, with this background and problem definition in mind, we can get into how we aimed at tackling this by going through a bit more detail on our framework. So, as Andy already mentioned, this is kind of an overview of how TG Talker works. So we have a two-part input. In the first part, we have a temporal graph that is encoded through the temporal graph encoding function G. And then we'll have the query that will be encoded through the query encoding function. And these two inputs will then be fed to a pre-trained LLMs. So we look at a few different families of models, and these LLMs will generate in the first part an answer to the link prediction query. And then given the answer and the graph in the query, will also generate an explanation to inform this prediction. So we'll go into a bit more detail on how each part of this process takes place. To do that, basically TG Talker is based on 4 core components, and we'll go through each of one in detail. The 3 first are there to basically supplement the LLM with the information it needs for the prediction. So we have the background set and the example set, and then some temporal neighbors that are getting sampled. And then finally, you have the query set, which has the actual queries that we're inquiring about. So starting with the background set, that's kind of the main context that we're feeding to the LLM. It's, as Andy mentioned, it's limited by the token length of LLMs. So it's usually a subgraph of the temporal graph that we're looking at. So it gives a recent overview of the graph that we're inquiring about. We then have also the example set. So this set is a set of usually by default, we're using 5 examples. And so these examples are question and answer pairs that will help the LLM learn how to follow our queries and how to answer them properly. So we have the questions, which are the queries as we'll ask them when we do link prediction, and then the correct answer for those queries. So with this example set, we're introducing in context learning, which, as I mentioned, is usually 5-shot by default. And these are also encoded through the same encoding function as the queries. And then a pretty important aspect to supplement the information to the LLM is the temporal neighbors that we feed it as well. So for each query, given a source node, we're going to feed the LLM with some of the most recent temporal neighbors of that source node, and that will help it make its prediction by providing additional context. So we usually go with 2 temporal neighbors, but this is also something that we can play around with. And then finally, we have the query set, which is the set of edges that we're actually looking to inquire about. And so we have these batches of usually 200 edges that we encode and ask the LLM to predict a destination for. So these are kind of the main components of the framework. You can see how they work together here. We start by giving the background set, and then optionally the in-context learning happens here, and we feed some temporal neighbors. And then with all of that, we're going to ask the LLM to respond to our queries and generate some explanations. To give a bit more of a concrete view about all of this, here are some examples of the prompts that we use as well. So at the top here, you can see the general system prompt where we kind of just inform the LLM of its role and its task being dynamic link prediction. We then have the general temporal graph prompt that basically just introduces the temporal graph, and it's introduced as well here with the background set. And then here you have at the bottom the prompts for the example and query sets, which are pretty similar. So you have the node that we're inquiring about, its temporal neighbors, and then the query itself. And as you can see in the example set, we also add the answer for that given node, whereas the query just has the question itself. So that's a bit of an overview of how everything works. And now we can take a bit more of a look at how that actually looks when we test it out. So to evaluate our framework, we looked at its performance on 5 different data sets. As you can see, we have them vary in size from 10,000 to more than 1,000,000 edges. Also in surprise, which is a measure of how unpredictable the interactions in the graph are. So we see that we have from 0.06 to 0.5, and also in duration. So we have graphs spanning from a month to 3 years. In order to test the TG-Talker framework comprehensively, obviously it depends on the underlying LLM. So we test different families of pre-trained LLMs to compare TG-Talker on. We have 3 families of open source ones. So we have 3 models of Quen LLMs varying in parameter size. We also test on a Mistral model and Llama 3. And then for the closed source LLM, we look at GPT 4.1 mini. And of course, we compare within TG-Talker frameworks between different LLMs, but also with TGNNs that exist in the literature. So we look at some that are event-based. Those are TGN, Tiantian, Graph Mixer. We also compare our results with the EdgeBank baseline. And then we also look at some snapshot-based models. So that will be HTGN, GCLSTM, and GCN. Some notes about comparing our model with these. First one is that these methods, as usual methods do, they predict a likelihood for every possible link, and that's different from how our method does that. So TG-Talker will, as you saw in the prompts, only output the one most probable destination node, so the one most probable link for the queried source node. And the second one is that conventionally, so as we mentioned earlier, conventionally temporal graph learning methods will be able to see the whole graph to make their predictions, but TG-Talker, obviously being limited by the token length, can't do that, so only has access to a recent subset of that temporal graph. So those are some important differences to keep in mind. So these are some of our results. So at the top here, we can see the different variants of the TG-Talker method. Then we have the event-based models and the snapshot-based ones on all of our data sets. So what we see is pretty encouraging. We see that TG-Talker achieves top 3 performance on all of the data sets, and especially top 2 performance on 3 data sets out of 5. This is especially encouraging because 2 of them are TGBL Wiki and Reddit. From the dataset statistics, those were ones with a pretty low surprise rate, so quite predictable. But then we also achieved top 2 performance on UCI, which on the contrary is the dataset with highest surprise. So that's a quite encouraging insight that TG-Talker can learn past superficial repetition cues and actually learn good patterns. As you can see here, we are outperforming most of the TGNNs except for Tiantian, which was also to be expected, to be fair, considering that Tiantian is quite advanced and uses more precise information, especially using common neighbor information from the source and destination node. If we compare within variants of TG Tucker itself, we see that in general the open source models perform better, and that in general higher number of parameters correlates with higher performance, which is also to be expected. As you can see here, the 8 billion variant always outperforms the 1.7 billion variant of Quen, and we see the trend generalize across all. So that's for the main results. We also conducted some additional studies. So first, we conducted an ablation study to look at the effect of each component of the framework. So as you can see here, we looked at the effect of removing in-context learning. So that's when we remove the background set, the example set, sorry. We also look at removing the temporal neighbors, which, as you can see, is the element that has the most impact. So it halves the performance on Wiki and it gets about 5 times worse on Reddit. So this is really an important component of the framework. And we also look at the effect of removing the background set and then all the components, which expectedly plummets the performance since the LLM has virtually no information to make its predictions. So if we look into more detail into this part, the temporal neighbors, I'll skip the slide because I've already mentioned all of the defaults. But yeah, we also looked at the effect of the number of neighbors. So as we saw, having no temporal neighbors really takes a hit on the performance. But we can see that that quickly changes. Even with one neighbor, we're already attaining like a pretty big boost in performance. And so we chose to settle on 2 neighbors because, as you can see, it's a good trade-off where we attain kind of the peak of performance while being less costly than if we sample 5 or 10 or more temporal neighbors. We see that this does, as expected, continue to improve performance as we grow this number. But depending on the data set, it's only marginal. It's the improvements from 2 to 10 neighbors is less than 1% on Wiki. So yeah, we chose this number as kind of a good trade-off between those 2 aspects. And so that's for the main performance, but as Andy mentioned, a pretty big motivation for using LLMs isn't just their performance and their like actual prediction capacities, but it's their explainability. So it's the fact that for a given prediction, we can actually ask the LLM to justify that choice and to provide a natural language explanation. So to do that, we had the LLM generate categories and generate explanations, and these fall into 10 categories. So these categories were developed by having an LLM go through the explanations that were generated and then make them fall into categories that we then ourselves refined. And here you can see some example of those. So for example, here we have the most recent interaction category. So this category, as the name suggests, it's when the choice was made based on the node that had the most recent interaction with the queried node. So it leverages the recency bias. Another example is the most frequent past destination, which involves counting neighbors, and this is for when you have multiple candidates, you can choose the one that appeared the most frequently in a node's history. So these are some examples of the explanations that we have, and we can look at into more detail at the composition of these explanations and the performance across these categories. So we can see here that we get explanations that are quite diverse in terms of their categories. We can see that the composition depends on the model. And so the pie charts show the composition of explanations, and below we also see the test MRR per category. So in the legend, you can also see all of the 10 categories that we ended up using. And as we can see, if we look at the performance across those, again, it varies per model. We can see that for Llama, for example, it's a bit more consistent in the performance across categories than for GPT. For example, llama always scores pretty highly on the orange, which is the new node pattern, which is a pretty encouraging insight as well regarding inductive capabilities. Whereas GPT, for example, scores higher on the most recent interaction pattern. So yeah, we see overall though a pretty high correlation between these categories and the predictive performance. And although that's a nice insight, it doesn't actually help us all that much to validate how good these explanations are and how useful they can actually be. So to solve that, we conducted a human annotation experiment as well. So this experiment was really conducted with the idea of assessing these explanations, how helpful and especially how accurate they are, if they're coherent at all with the actual patterns in the graph. So we asked three independent annotators to assess 50 links that were correctly predicted, and we reproduced that on two data sets, so TGBL Wiki and UCI. Again, TGBL Wiki was one of the ones with lowest surprise and UCI with highest surprise. So this was with the aim of gaining insights that aren't just that are generalizable across different predictability levels, let's say, of data sets. So we asked the annotators to do two things. First, to categorize the explanation. So each annotator was provided with the link, the 50 links, and the corresponding explanations. So we asked them to categorize that explanation in one of the four of or 10 categories, and then to assess the correctness of that explanation. And by assessing the correctness, of course, as Andy mentioned, we don't really have a ground truth of why links happen. So this is more by asking annotators to look at the temporal graph, the same that is provided to the LLM, and to make sure that the explanation is based on actual patterns that happen in the graph. So when we asked annotators to categorize the explanation, we saw a pretty high rate of agreement between the human annotated categories and the LLM generated ones, being above 75% on both datasets, which is really encouraging. To validate that finding, we also looked at the agreement between annotators themselves regarding category attribution, which was also pretty high, higher than 60. So we got a substantial agreement here. And then looking at assessing the correctness, so we asked annotators to assess the correctness of the explanation on a scale of 1 to 3. So 1 being an explanation that's completely incorrect. So that would usually be a case where you can notice hallucination in the explanation, for example. And 3 would be completely correct. So again, we don't have a ground truth, but that means that it's based on information that we can actually see being reflected in the temporal graph. And again here, pretty encouraging levels of agreement. So for the average correctness on both data sets, we're above 2.8 out of 3, which is really high. And if we look at the intra-annotator agreement again for those ratings, it's even higher than previously. So it's above 75% on both data sets, which really validates these findings. And then we also asked annotators, especially when they would give a correctness of 1, to flag the explanation if it seemed to be hallucination. So if it mentions patterns that didn't exist in the temporal graph, links that weren't provided, etc. And we see that those rates are pretty low. So it's only 2% on Wiki and 6.6% on UCI. So all of these findings are pretty encouraging for this work, but also in general to motivate the use of LLMs. We can see that the explanations that they generate make sense and are pretty solid. So this is all pretty encouraging. And yeah, that's an overview of our project. Thank you very much for listening, and I hope you have questions and enjoyed the talk.
Yeah. Yeah, thanks, Emma. There's actually a ton of questions in the
Yes, I saw notifications. I haven't been able to read them. Let me
Do you want
take a
to
look.
answer some of the clarification ones, and for the more researchy ones, I can take
Mhm.
take a 2 cents on it.
Sure. Let me just scroll up. Um,
Um,
So, Zach, regarding whether there are explanations in the few-shot learning examples, they're just question answer pairs. So we have the query and the destination node that goes with that query. We don't have explanations for those, partly because we don't really have ground truth for explanations. So we couldn't be able to provide explanations that we're sure will help the LLM learn what we want it to. I see you have your hand raised. I don't know if you have other questions, Zach.
Yeah, I had a quick question on the background data that you provide, because related to the scalability question initially, like you can't put the whole graph in, right? And all the temporal data, but it seems implicitly that whatever you put into the background is sort of the candidate set that the LLM can choose from to predict the target. So I'm wondering how you define that background set and make sure you get the right potential targets in there.
Yeah, so I mean, we're definitely limited by the LLM performances, so this will get better when they improve. But right now, we have a default background set size of 300, so we just take the 300 most recent interactions. So we are leveraging the recency bias as we build that set, in hopes of
and
giving better candidates.
also,
Yeah.
also technically the temporal neighbors. So as you see in the ablation study, the temporal neighbors plays a huge part. So basically so if you think about the receptive window of the LM, it takes a few hundred temporal edges, most recent to your prediction, and then plus the temporal neighbors. What we see is that the temporal neighbor part is really making it work, have much higher performance. So at the initial stage, when we just have the background set, we find that it's not as good as TGNNs, but as soon as you have temporal neighbors, the LMs can outperform most TGNNs. Um,
Maybe I'm confused by the words then. So by temporal neighbors, do you mean the temporal history of the neighbors of the source node?
exactly.
What is a temporal? Okay.
Exactly. So
And then
basically, you use the standard temporal neighbor sampling that TGNNs do. You sample these neighbors. So we use a recency sampler. So you keep all the neighbors from the past, and well, not all the neighbors. Like you keep like five most recent neighbor or something, right? So and you feed that to the LLM, saying that this is your past neighbor.
got it. Thank you.
Yeah. And also, I think going back up more for the questions, I think there's a question from Hussein um, about the textual encoding of the graph impact the performance. So on this, I will quickly answer. So the text encoding of the graph, which is basically how you choose to construct the prompt, actually is quite important. We have went through different versions. I think this version is the one that we find that works best. But yes, so basically we provide a template for future research to keep using and improving upon, but it does play a factor. Um, and in my opinion, you want to be as straightforward to the LLM as possible about what you ask them to do. Like, so we show the example prompts, like basically you want to say, you are a temporal graph learning expert, and here are the temporal graph in this format, specifically source, destination, node, timestamp. So you kind of be very explicit about what information you are providing to the LLM. Um, and yeah. Um, what's the next question? The hallucination one. I think we answered that one. If you go to the hallucination slide, Emma.
Um, yes. Do you mean this
Yeah,
one? Yeah.
yeah. Um, Yeah, so here we see that LLM actually doesn't hallucinate that much. So here we are mostly using this one is the GPT one that we evaluated. It doesn't hallucinate that much, but um, one thing I want to point out is we observe that, but it's more like an empirical observation is that the LLM will tend to hallucinate when it doesn't find the correct thing in the context. Like if it doesn't know what to answer, of course it's going to hallucinate. So that's kind of intuitive. And in cases, you will have these naturally occurring in temporal graph as well, because sometimes you will have a new edge between two new nodes you never see before arrive for the first time. Then the LM doesn't know what to do with it. right? It can try to make guesses, but it's still going to hallucinate a bit because it doesn't know how to deal with that. Um, so, so that's a very good question. Um, have a lot of neighbors, the model hallucinate new node IDs. Um, the model, this we haven't checked systematically, so there are some hallucinations as you see here, but we haven't checked this particularly kind of like systematically. Um, but I think it's also possible for the models to recognize patterns kind of in the node IDs potentially, but I'm not too sure about that. So potentially more things to investigate there. How would you encode node and edge features? So I can also quickly take this one. So we currently do not directly encode that, but intuitively, if you have text-based node or edge features, it's very easy to add. It's not a problem at all. You can just add to the prompt. If you have numerical and so on, I think you would need some other ways to deal with that. It's not directly clear what's the best way to do that. Um, okay. Yeah. So maybe we'll take Julia's questions before we take more of the Zoom ones. We can go kind of back and forth. Yeah.
I had a question on, could you go back to this explanation slide, please, where you have this little chart with the different explanation types? Yeah, this one.
This one or the examples? Yeah.
No, this one is great. So I thought it was very interesting to see the explanation categories. For example, there's this repeated interaction, no, most frequent past destination, and I think most recent interaction. We did something somewhat similar for knowledge graphs, and there we had a chance to learn whether like most recent is more important or most frequent is more important, depending on the relation type. Like winning is more important, the frequency and so on. But in temporal graphs, you don't have this relation type kind of information. You only just have the node IDs and the path pattern. Do you have any idea or intuition or finding on how the LLM decided for which kind of category it would go for to make its
Yeah,
decision?
so between those two specifically, and this is more like from looking at it ourselves and systematic findings we have, but the most recent interaction pattern is a lot more frequent when you have one candidate. So when in the provided history you have one node that was pretty recent, and then most frequent past destination was more common when you would have multiple candidates and you would have to choose between one. Then the LLM would be like, okay, then it makes sense to look at the most frequent one out of all of those.
Thank you.
Okay,
Um, okay. So
thanks.
yeah, on that point, I think if you feed it edge type information, uh, Julia, I think it could be more nuanced in terms of explanation. Potentially because it could incorporate that into the explanation, right? It could say that for this edge type, I predict it's most recent because for this edge type, this makes sense to me. To like I should pick the most recent like versus the most frequent and blah blah blah. And also another thing that we find out from the explanation category, if you take a look here, the dominant ones are actually the ones that we have in the current heuristic. Like we have the uh, um, I think you have a baseline as well, like Julia, that's also like recency and mixed in. I forgot exactly the name, but also we had the edge bank for standard temporal graph. Basically, the LLM is learning to do these heuristic kind of by themselves a bit. Um, and also doing a bit of other stuff. Like you can see that there's interesting things like most common node, the yellow part, right? So yellow part is like the LLM don't know what to do.
Yeah.
And basically, what do you predict if you don't know what to do? So you predict the most common node, like the most popular destination. So that
Yeah.
makes sense, right? So it's kind of trying to do its best effort guesses, kind of. You can see from the explanations. That's pretty interesting.
Yeah, I also thought it's pretty interesting that you have pretty good results and still the reasons for that results are still those like rather easy pattern to be found, just a smart way of doing them. That's quite interesting.
Depends on the data set, right? So you can see that the LLMs are not performing the best TGNN. It outperforms most TGNNs, but it doesn't perform the best TGNN because best TGNN also have additional information and also potentially a larger context than LLM does. And one last thing on the explanations, there's this sequence or alternation logic stuff. So this part is also interesting. I read some example explanation from this category. Basically, the LLM will say that if you purchase, so like for example, like more like real world example, like you purchase a pen, a paper, and some ink, like ABC in sequence. Then when you purchase a pen and a paper, the next thing you will purchase next time will probably be ink as well because you have these sequence. This is something that's not modeled by any heuristic that we have right now in temporal graph, based on my knowledge. And the LLM is kind of learning these things just by themselves, basically. I find that to be pretty interesting. And yeah. And we can go back to more questions. Um, let's see, I lost track a little bit. Okay, so let me see if this is the most recent one. Um, so Victor, you have some question as well, right? Do you want to ask?
I'm currently in a train, so maybe you
Okay.
can read it.
So yeah. Okay. For the explanation, are you doing two LLM calls or a single LLM call? So currently our setup is that you make prediction with one LLM call and you feed the prediction to the prompt. So that's the temporal link explanation definition. You feed the predicted link, so not necessarily the correct one, but you feed it and plus all the context from before, and you make a second call which just asks the LLM for explanation. We do this way because, first of all, we don't know what's the correct way of to do it. This is the first work that actually, I think, possibly the first work to look at explanations for graph task. And we don't know what's the best way to do it, but the practical implication of this is that sometimes with LLM, it can generate a long sequence of answers. So by separating it to two LLM call, it kind of more modularize and separate that part. So, but I think theoretically you could just do a single call and say, give me the destination, but also give me the reasoning for that. So I think that's possible. But in terms of performance, we haven't tested explicitly for it. And yeah, prediction. Yeah, so and you always do prediction first, and then you feed the prediction into the explanation as context to ask. And we have a bunch of note summary. And I think that's all the questions, right? Is there any more questions? Okay, we have a follow-up from Victor. Reasoning first because we've seen these chain of thought style. Okay, we tried chain of thought. For what we tried initially with the smaller open source models, we don't see that it helps too much with performance for chain of thought. And the model sometimes will go in loops. Basically, it will just the chain will just keep going and never go to a destination. But this could be different for larger language models. So I think how well this works also depends on the model size and how your model works. Yeah, and yeah, at least initially we didn't find it to be too helpful with the chain of thought. Okay. Okay, I think that's all the questions. Thank you, everyone. And happy to chat more. If you have more questions, feel free to send me a message on Slack or just reach out to us. And yeah, thanks for coming to the talk, everyone.
Thank you.
Thank you. Bye.